Welcome to solverfy.
.58. So these three radioactive materials that occur in granite in sufficient quantities to contribute to the heating of the Earth. So there's a lot of granite, and you can imagine that if this produces a substantial amount of heat per kilogram of granite, then you multiply that by the number of kilograms of granite on Earth, and it can produce a lot of heat. And that's exactly what we're going to be doing in this problem. So in part A, we're going to show that the power per unit mass of granite is going to be 1 times 10 to the negative 9th watts per kilogram, which doesn't sound particularly auspicious. But then in part B, we'll see what the total power is and compare it to the power received from the sun. And then we'll see how they compare. So the rate at which energy is being released by these decays is just going to be the sum for each of the isotopes of their rates each one contributes times the energy released in each decay. And this is the total all the way to its final stable endpoint. So this is going to be the decay constant times the number of them present. So that's R is equal to, again, times this decay energy. Now we're told their half-lives, so we need to rewrite this as the natural log of 2 divided by their half-lives, 1/2 I. Now the number of each thing we have is going to be our sort of sample mass in question times the fraction constituted by the element that we're in the sum term of, divided by its mass. And since Q is something that's just given to us in the table, we don't need to go and do anything with that. And we see that this does in fact turn out to be 1 nanowatt. Just putting in the numbers here. Note that these are in parts per million, so like when you put this in, it should be 4 times 10 to the negative 6th, etc. So we're told that we have 2.7 times 10 to the 22 kilograms of granite on Earth. So we multiply that by our 1 nanowatt per kilogram. And we get a pretty respectable, 2.7, of course, times 10 to the 13th watts. It's distributed all over the Earth, though. Maybe not evenly, but because, like, in the ocean, floors are basalt rather than granite for the most part. So this is a total of... Wait, why did I put a negative sign there? No. The total of 2.7 times 10 to the 13th watts, which the problem says that it contributes significantly to the heating of the Earth, but also it does turn out to be much less than the 1.7 times 10 to the 17th watts from the sun. So although it's a large amount of energy that's being added, the sunlight is still providing most of the heating of the Earth.